Hi. Good to see you guys, as always. I would like to say a few things about Lagrange multipliers. That's the subject of a lecture on Tuesday. When we talk about Lagrange multipliers, there's one important aspect which one has to realize, and that aspect has to do with whether the curve we're dealing with is bounded or not. Okay? So the example which we discussed in great detail last time was the example where the curve was an ellipse. An ellipse is bounded. Now, what do I mean by boundedness? It's bounded because it can be, it is contained in a disk of a large enough radius. Okay? So in this case, I think this was 1 and this was 1/2, and this is -1, -1/2. So we can take a disk of radius 1, and this entire curve will be inside. Or if you want, take a disk of radius 2, even bigger. So for sure it will be inside. In other words, there are no branches of this curve which go to infinity. Okay? An object is called bounded if it is contained entirely in a large enough disk, or a ball if we are in three-dimensional space. Okay? So these curves are, this kind of curve is bounded. And for bounded curves, the method works in the best possible way. In the best possible way, namely, we will be able to find the maximum and the minimum of our function. Our function will have a maximum point, which was here, and a minimum point, which was here in our example. But if the curve is not bounded, then it may not have a maximum or minimum or both. Okay? So that's an important remark that I wanted to make. Because actually, on the homework, as you have probably already seen, there are some exercises where that is the case. Okay? So let me contrast this to the following curve. And this is actually exercise number 3 in 14.8. I know it's on the homework, but okay. It's my gift to you. Okay, well, if you like it, I can do it again. Maybe next week or a couple of weeks. All right. So in this exercise, the curve is given by the equation xy = 1. Okay. So what is this curve? This curve, well, to understand that, it's best to rewrite this equation as in a more familiar form, y = 1/x. If you write it in this form, we see immediately that this is a graph of the function 1/x. And that's what we call hyperbola. Right? So that's actually something we learned a long time ago. And it looks like this. It has two branches. One here and one here. So this is a point 1, 1. And this is a point 1, -1, -1. Right? And in this exercise, you're asked to find the maximum and minima of the function f of xy, which is x squared plus y squared. Okay? So this curve is not bounded. So while this was bounded, this is unbounded. Why? Because it's, well, intuitively, because it goes to infinity. It has branches which go all the way to infinity. More precisely, no matter how big a disk you take, it will not be contained. This curve will not be contained in that disk. There will still be some points outside. So it is not bounded. And that changes the equation, so to speak. It changes the game. So let's see what are the maximum and minima. So let's apply blindly just the Lagrange method and see what we get. So Lagrange method tells us that nabla f, we should look at the equation nabla f equals lambda times nabla g. Right? So in this particular case, the function f is x squared plus y squared. So this is 2x 2y. And the function g is xy, right? Because the equation is xy = 1. This equation. So we get lambda times y x, right? And then this corresponds to a system of two equations. 2x equals 2x is equal to lambda y, right? And then you have 2y equals lambda x, right? So from the first equation, we find that lambda. Actually, it's better maybe to. And of course, there's a third equation which I forgot, which is xy equals 1, right? And so from this, let's do this in the following way. So let's say that let's find y is 1/x. Right, and so let's substitute this in both of these equations. So we get 2x is equal to lambda times 1/x, and here 1/x is equal to lambda times x. Right, and so so from this we can find that lambda is equal to 2x squared. Right, and so then we substitute in this 2x squared, so we get 1/x is equal to 2x cubed, right? Which means that x to the 4th is equal to 1, which means that x is equal to plus or minus 1. Right, so far so good. Okay, so now we find 2 points. We find 2 points. One point is 1. When x is 1, we use the second equation to find that in this case y is also 1. And the second is -1. And then again y is also -1. And then let's evaluate the value of the function f. F is x squared plus y squared. So we get value 2. And then here we also get the value 2. So that looks like a puzzle because we just follow blindly the method. We find 2 points. So we think, well, perhaps one of them is the maximum, the other one is the minimum. But when we evaluate the function, we see that the values are the same. So what does it mean? Does it really mean that the maximum value of the function is 2 and the minimum value of the function is also 2? That would mean that the function is constant, is equal to 2 everywhere. But the function is not constant, right? It's x squared plus y squared. Right? For example, it is actually equal to 0 here. I mean, or it's not even constant on the. That's not a valid argument because we have to look at the restriction of the function to our curve. But the restriction of the function to our curve is x squared plus 1/x squared, right? So again, it's quite clear that the function is not constant. So what happens? So to see what happens, I mean, so far I just did this calculation blindly, so I didn't like that's what you would do without drawing the picture. You just do the calculation, and then you see, oh gosh, I got this. The answers are the same, so that's strange. What really happened? So now let's find out what happened. So the best thing to do is to go back to this, to how we actually derived the Lagrange equations in the first place. When we derived the Lagrange equations, we looked at the level curves of our function. In this case, the level curves are extremely simple. They are x squared plus y squared equals k. And this is, of course, the equation of a circle of radius square root of k. So the level curves are concentric circles of all possible radii, right? And there's more. There's more and more and more. So each of the circles represents the set of points for which the value of the function f is the same. So for example, the function takes the same value on this circle. It takes the same value on these circles and so on. So which means in particular that the function is the same here and here, right? And here and here, which are the points of intersection of that level curve with our curve xy equals 1. So now if you just look at this, you see that the value of the function f increases as we go outward. As we go outward, the radius of the circle becomes larger. And because the function is essentially the square of the radius of the circle, it grows when the radius becomes larger. And likewise, it becomes smaller when the radius becomes smaller. But because the curve is unbounded, you see that this function doesn't have a maximum. Right? Because any positive real value greater than the value at this point will actually be realized. And the value at this point is equal to 2. Right? Any value will be realized. If you want a value, a million, the value million will be realized, or maybe twice million will be easier. Right? So then it will be like x and y equal to 1,000. You'll get two times a million. So any value will be realized because the curve is unbounded. So then the question is, so that means that the function actually has no maximum. This function has no maximum. A maximum value. On this curve. So what about these values? Well, these values are realized at these 2 points, which I have marked in the beginning. And this actually, you can see that these are the smallest possible values because these are exactly the points where the level curve for f touches our curve. Right? The level curve for f is a circle, and it touches our curve of the hyperbola at this point and at this point. So this is really the smallest value, the minimum value, because if you take a radius any smaller than this, you will lose contact. You will lose intersection with our curve. So therefore, this is really the smallest possible value. So I went through this argument in great detail on Tuesday. I will not repeat it. So that argument is valid for these 2 points. And this argument shows that this is indeed the minimum values. So it's not surprising that the 2 values are the same. Right? So they just both are attained. Both give us the minimum value. Now, it could happen, for example, that I could just change the setup, and I could consider instead a curve where the top branch, the right top branch, would be going here. So it wouldn't be given by this equation, but it would be a union of 2 curves. One say would be xy equals 1 in the third quadrant, and the other one would be xy equals 2, for example. Right? So then it would actually be higher. So in this case, if we apply Lagrange method, we would find again 2 points, but the values would be different. So in that case, again, we compare the values. So if, for example, as a result of this calculation, you could actually get 2 and 3, say, if you chose the function a slightly different way, you could get a different value. And then it would be even more tempting for you to say, okay, this is maximum, this is minimum. But actually, it would not be, this answer would not be correct. One of those 2 answers would be minimum, namely the one which is smaller, right? But the function still would have a maximum because the branches go to infinity. Okay? So in other words, don't think that the fact that they're both equal is the only possible scenario for which indicates that the function doesn't have a maximum. You could even have 2 different values, but both of them, say one of them would be minimum, one of them would be neither maximum, minimum, and no maximum. It's also possible. Okay? So these 2 are actually 2 minima. Finally, there is a possibility that the function doesn't have either maximum value or minimum value on a given curve. For instance, let's take the function y. So let's say just half of the hyperbola. Let our curve be y equals 1 over x and y greater than 0. And let's take as function f, let's just take y. We can do that, right? So in this case, clearly there is no maximum value because it goes to infinity, right? Same reason. But there's also no minimum value for a slightly different reason. It's not because the function goes to minus infinity the way it goes to plus infinity, on this part. It goes to 0, so you might be tempted to say that the minimum value is 0, but you can't say that because that value is never attained. The value 0 is never attained. You get as close as possible to it, but it's never attained. So that means that there is no minimum value because the 0 value is not attained, and any value which is above 0 is attained, but it's not the smallest one because you can always take on half of it, and you get smaller value. Right? So this function has neither a maximum nor a minimum. So in other words, to summarize, it is boundedness which guarantees the existence of maximum and minimum. If you have a bounded domain, you will always have a maximum and a minimum. If the domain is not bounded, or curve is not bounded in this case, all bets are off. Anything can happen. You might have only a maximum but no minimum, only minimum and no maximum, or neither. Finally, keep in mind the following thing, that here I wrote this equation just by itself, right? Just by itself. I did not put any limits. I didn't say what are the ranges for x and y, right? So if there are no limits, it means that they could be arbitrary. That's why I drew the entire hyperbola. But there could be variation on this problem where, let's look at this problem, and let's do the following variation on this problem, where I would also say y equals 1 over x, but I would actually put explicitly the ranges, say x is between 1 and 2. And then I will ask maximize and minimize, or find maximum and minima of the function f of xy equal y. If I do that, then my curve is not the entire hyperbola, or not the entire branch of the hyperbola which is drawn over there, but only the part between 1 and 2, right? And the part between 1 and 2 looks like this. So this will be the 2 endpoints. So this is 2, and this is 1, and this is 1, and this is 1/2. So in this case, you see the curve actually has boundary points. So it is just like when we minimize functions in one variable calculus on an interval, which includes the endpoints. So in this case, the maximum minimum could well be attained at the endpoints, which is what happens here. Here, the maximum does exist. It's at this point. Because since I imposed this condition, I cannot go any further. In the previous example, I had the entire hyperbola, which went to infinity. It was unbounded. This guy is bounded. It is certainly sitting inside a large enough disk. right? This curve is bounded. So there is indeed a maximum and a minimum. And the maximum is when x is 1 and y is equal, in this case y is 1. So let's just write f is 1. And the minimum is at x equal 2. In this case, f is 1/2. Okay. Any questions about this? So I try to give you several representative examples to give you an idea what are the possibilities. And you should keep these possibilities in mind when you do problems like this, when you solve problems like this. Usually there's no way of telling, for an unbounded curve, there's no way of telling whether the points which you find are maximum and minimum, just from the algebraic analysis like this. You really have to visualize the picture. You have to use some ways to reason to argue why it is maximum or minimum. In this case, for example, let's say you don't want to draw the picture. You could argue as follows. You could say, okay, so both are the same, which means that, well, we know the function is not constant. Both are the same, so it could be either maximum or minimum. Which one is it? Is it maximum or minimum? Well, on this curve, I could find a point for very large x. So let's say x is 1,000,000, and y would be 1/1,000,000, so it's like really small. So the value would be 1,000,000 squared. So on this curve, I can find a point where the value is 1,000,000 or 1,000,000 squared, right? So which is greater than 2. So that means this is the minimum and not the maximum. So that's one way to argue even without drawing the picture. But you have to have an additional argument to say which one is it, maximum or minimum. Okay. So let's move on to the next subject. And the next subject is integration. I promised you at the beginning of this course that we will, or maybe not promised, promise is not a good word, but I told you, I gave a preview, and I said that essentially you can break the material into two parts. One is integration and the other one is differentiation. These are in some sense two opposite operations that we do in calculus. What we studied in the last few weeks was the differential calculus. We studied things related to differentiation like Lagrange method, where to find the maximum and minima we had to take derivatives. We had to take partial derivatives, for example, and then solve some equations. And now for the next few weeks we will talk about integration. Okay, so today is the first installment of integration. So what do we need to know about integration? Well, first of all, I would like to recall, as always, what we learned about integration in one-variable calculus. Actually, we already talked a little bit about this before, so I'll be very brief. In one-variable calculus, we are used to calculating integrals of a function one variable over an interval, say from a to b. So there's several things that we learned in that regard. The first thing that we learned is that in the case when the function is non-negative on this interval for x between a and b, so let's say this is a and this is b. So if the function is non-negative, then the graph of this function is going to lie entirely over this interval, or more precisely, the part of the graph above this interval, or corresponding to this interval, will lie above the x-axis. In other words, I want to avoid a situation where it's above and below the x-axis. I'm not really losing much generality by assuming that, because even if it were below, I could just add a constant, sufficiently large constant to the function, and raise it above the axis. And so then the integral will be different from the original integral by the integral of that constant. But the integral of the constant we know. It's that constant times a times d minus a. So we don't really lose much generality by assuming here that the function is non-negative on this interval. And if it is non-negative, then actually this integral represents the area, what we call usually informally under the graph. And when we say under the graph, we mean between the area of the region bounded by the graph, the vertical lines y equal a and y equal b, and the x-axis. Oh yes, x equals, that's right, sorry. Thank you. X equals a and x equals, sorry. X equals a, x equals b. This is y equals 0. And this is a graph, which is y equals f of x. All right, so that's the first aspect, that this is the way integral gives us the area under the graph. That's number one. So you see, function is in one variable. The function is in one variable, but you get an area of a two-dimensional object. You start with a function in one variable, but you naturally get a two-dimensional region because you look at the graph, and the graph lives on the plane. You add one more variable y, and then you use the graph as a boundary of this region. So you get a two-dimensional region, and it has an area, and that area is represented by the integral. Okay, so that's the first aspect. The second aspect of this, of the study of the integrals, is how do we define it? So the first aspect is what does it represent? And the answer is it represents the area. The second aspect is how do you define it? And the way to define it is somewhat subtle. The way we define it is we break this interval into smaller pieces, and then we approximate the function by the step functions like this, by just constant functions on each of these intervals. Right? And so on. And that gives us the possibility to approximate the entire area, this entire area, as the sum of areas of all those elementary rectangles. So let's say here the one rectangle will look like this. One of these rectangles will look like this, where this side will be delta x, and this side will be delta y. Say. It's actually not a good idea. Let's call it. It's just going to be f. Let's say this is the point xi in the partition. This is xi plus 1. This will be f of xi. And then the point is that we don't know a priori at the beginning what the area of this complicated region is, but we certainly know what the area of this one is. And the area of this one is f of xi